Hey classes, welcome back. I'm talking to you without the microphone on today because I'm going to have to write on the board just a little bit. I want to give as quick as I can a recap on what we did in class today, hopefully getting us into the whole idea of chemical reactions, especially later on when it relates to photosynthesis, the most important chemical reaction we'll be talking about all year. But then also when we're talking about molecules, when we go into the atom, when we go into the cell, and how the cell puts together different atoms to make certain molecules that are absolutely critical for life, proteins, lipids, carbohydrates, that sort of thing. So let's jump on in very, very quickly. First of all, a couple quick reminders. Don't forget, take the quiz that's out there right now. It's out there starting from Wednesday all the way through Saturday. And there is an optional extra credit / makeup. If you have any missing quizzes, this is your chance to get one down. Or if you want to improve one of the grades from one of the previous quizzes that we had, if you take the optional quiz out there, and it's better than one of your previous ones, that will take its place in the old grade book. If you don't do as well on it, it won't bring down your grade. It only is a one-way trip, so give it a shot. It's also good to review what we've been doing in class anyway. And then class comments on the everyday work. Unfortunately, had to get turned off. If you look also at the coastal cleanup, want a little extra credit, you can send me a pic from you doing the coastal cleanup. I'll be out there as well. I know Mr. Martin's going to be out there. I believe Mr. Leek will be as well. So see you at the coastal cleanup this coming weekend. All right, let's jump on in. Yesterday we saw a little bit with the Hindenburg of all things. Now the Hindenburg comes in for a couple of reasons. One, the Mythbusters actually do a myth specifically about the Hindenburg. And so we use a tiny bit of that in class when we're talking about chemical reactions. And then also the little bit that we saw today on uranium. We were watching a great special by Derek Muller on the element uranium, how uranium really changed the entire world. It brought us into the nuclear age in terms of us understanding its properties. And that's one of the things that we have to learn about, because the radiation that comes off of uranium and other radioactive elements is how we do everything from treat certain cancers to when you go to the dentist and they fire higher energy photons through your head to get an image of your teeth. That is done with radioactive isotopes. So that's why we're learning, some of the reasons we're learning about those things. We wanted to turn you into a chemist today by doing our very, very first chemical reactions, talking about the hydrogen gas that was coming out of the Hindenburg and relating it to our conservation of matter. So let's get to the whiteboard here and show you what I mean. I'm going to need a blank whiteboard for this one. So this is what it looked like basically in class today when we're talking about this reaction and how it related to the conservation of matter. So remember, this year we're using blue for hydrogen. Now in the model kits, they often use white for hydrogen. Red is almost always used for oxygen. Black is almost always used for carbon. But the only reason I'm using blue, one, it stands out a little bit better than just having a white circle, and it's one of the colors that came with my my kit here. So I'm going with blue for hydrogen all this year. If you check out, and I'm just going to make the circles right here and not color them in. Well, I guess I'll color them in a little bit to make it kind of stand out on the video as I look back at the screen there. You have one hydrogen molecule cruising around inside that large Zeppelin, that large blimp, the Hindenburg that we used as the example in class the other day. And at some point or another, we don't know why, it starts leaking out and it runs into, and I'm going to use the red, and the students should have used the red as well, an oxygen molecule here. Now here's the thing, as the hydrogen molecules, and it's diatomic, which is a fancy way of saying that it likes to travel in pairs. You almost never see, when they're writing hydrogen gas, just H for hydrogen. It's usually written as H2 because hydrogen likes, if you will, I'm humanizing it here, it likes to travel in pairs. Oxygen is the same way, also a diatomic molecule. It's traveling in pairs in our atmosphere. This oxygen that is floating around our atmosphere, about 18% of our atmosphere is oxygen, has been put up there by photosynthesis for the most part. And as the hydrogen runs into the oxygen, nothing happens. They run into each other and say, hey, how you doing? How you doing? They just kind of pass each other. Nothing is going on until, and this is the important part, until some type of spark happens. Over on the previous board, we talk about activation energy. In a chemical reaction, you have to have something to get the reaction going, to make it so that these molecules interact with these molecules and switch around partners. When we're talking about atoms and we're talking about chemical reactions, one of my very favorite physicists, Richard Feynman, compared them to kids building blocks in a room. If you have a daycare, all these building blocks are getting thrown all over the room in the daycare. If you start the day, say, with 100 blocks in that room, as long as none get thrown out the window or no kids take them home, at the end of the day, even if some are underneath the furniture or if they've been put up on shelves, you're still going to have 100 blocks. Atoms are like that too. In other words, if you think of atoms as being like perfect building blocks, they're going to always, at the end of the day, be the same number of atoms in chemical reactions at the beginning as there were at the end. If you look, for example, at the piece of paper that I'm using right here on my desk, part of it's been ripped off. In each of the classes, I ripped off a little piece of paper. I lit it on fire. We burned just a tiny, tiny bit of the paper off and let it burn out, showing two things. One, we didn't really destroy any atoms. We just moved them from one place to another place. There's still the same number of atoms we began with. I couldn't destroy atoms with just a simple lighter. And two, just like when we dipped a little bit of dye in water the other day in class, very, very quickly, after maybe a minute, the students at the back of the classroom could smell the little bit of paper that we burned up here at the front of the classroom. A great example of diffusion, molecules constantly moving and bringing other molecules with them as they move through a fluid. Okay, back to this right here. When we had the reaction happen, again, we don't know why the hydrogen was leaking from the Hindenburg blimp, the Zeppelin, but it ran into the oxygen, and it made, after releasing heat and energy, water. So H2O. Now, the one thing that students often ask, I get this question quite a bit, well, wait a second, if it was making water, why didn't that put out the fire? There wasn't enough of it to put out the fire in terms of the amount of heat that was being put out by this chemical reaction. So we draw in our notebooks a water molecules. Again, it's red for oxygen, and we have to attach two hydrogens to it. And once we draw those in, hey, we've got a water molecule. Challenging the students now in class to think about this. Wait, just a second. I've got two hydrogens over here. Two hydrogens over here. That's okay. There was no more hydrogen created. No hydrogens magically went away. But now I've got two oxygens here and only one oxygen over there. We're going to have to do something to change this. Visually, it looks a little bit like this. To get the oxygen number up on the right side of our equation. In other words, this reaction yields, yields is a chemistry term, makes or yields what's on this side of this, the reaction, the products we call that. I have to draw another water molecule to kind of help it even out. So I'm going to color in one more red atom there for my oxygen. Go back to my blue pen. And color in that one right there for hydrogens. We're close. We've got two oxygens now. That seems to work out pretty well. We only have two hydrogens over here. When we're looking at this, the chemists would call this balancing the equation. We're going to have to do something without splitting apart anything that's on this side already. We're going to have to add another molecule. Well, we're going to add a hydrogen molecule. Looks something like that. 1, 2, 3, 4 hydrogens over here. 1, 2, 3, 4 hydrogens over there. Hey, that balances out. You'll be doing lots of this in 8th grade in the high school chemistry. 1, 2 oxygens here. 1, 2 oxygens here. What would this look like if I were to draw it out as a chemical equation? Well, let's do that. I've got two hydrogen molecules here combining with one oxygen molecule. Notice how I don't bother putting the 1 here. It's like in algebra class how if you have two x's, you put the number 2 in front of the x. However, if you just have one single x by itself, one variable by itself, as a general rule, we don't write that 1. It's just an x. So one single oxygen yields or combines to make 2 water molecules, 2 H2O. So the dramatic film, the Hindenburg coming in and unfortunately catching fire, crashing to the ground, that dramatic film really was capturing this chemical reaction. H2, O2, H2O, it makes water. That whole thing just made water. Again, not nearly enough water to counter the heat that it is caused by this reaction to put out the fire, but that was a very, very basic chemical reaction. The other one that we also introduced to some of the classes, I'll put this out there on the notes, but I won't go into too much detail on it yet. We'll do it next time on our next video, and I'll put it on the online notes as well. We had one more molecule that we're going to have to learn. This is CH4 methane. I challenge students to draw that as a carbon, a black colored in circle with 4 hydrogens, 4 blue colored in circles around it. Combining with oxygen, so it's methane combining with oxygen to make carbon dioxide and water to yield CO2 and H2O. CO2, global warming gas. CH4 methane, also a global warming gas, but much more potent in terms of the amount of heat that it traps in our atmosphere. So those are going to be important to learn later. I think over the course of this year we learned about a dozen molecules, and we've already had 5 or 6 of them right here. We've had carbon dioxide, methane, oxygen, water. We'll be going into, of course, DNA, lipids, proteins, carbohydrates, things like that. Finally, the last thing we saw in class is we checked out our video on uranium. The difference between a nuclear reaction and a chemical reaction. Now, nuclear reactions, you can have, at the end of the reaction, less mass than you began with. This is what powers our sun. Again, very, very simply, you've got hydrogens, 2 hydrogens combining to make a helium, but, and again, simplifying that a little bit, but you've got a helium that weighs a little bit less than the original hydrogens that made it. And how is that possible? With this equation right here, the very, very famous E equals mc squared. I just wanted students to have in their notes that c is a constant, means the speed of light. And when you're talking about conservation laws, it's not like we throw conservation laws out the window when it comes to a nuclear reaction. It's just that in a nuclear reaction, you can turn some matter directly into energy, and we have to account for all the energy and all the matter that's in any reaction to make sure that we have at the end of the day exactly what we began with. If you have anyone in your family who's an accountant, it's kind of like a sheet at the end of the day. You've got to make sure you've got exactly the same amount of money that you began with. So in our little video clip, about 10 minutes long on uranium, the whole point of the uranium video clip was to show a contrast, to compare it to a chemical reaction. Chemical reactions, perfect Legos, recombining at the end of the day, they can recombine lots of ways. The mass is going to be the same. In a nuclear reaction, you're not going to have the same mass that you began with. That's the main difference. That's the main thrust of what we did. Again, the very, very quick recap was on the chemical reaction that we saw, making sure that at the end of the day, you've got the same number of atoms and the type of atoms on the reactant side versus the product side. That's where I'll leave it today. I'll put these notes out there online. That's about as deep as we're going to go really into chemistry. And then next week we jump back into the book in terms of the biology. What does it mean to be living? How do we know if something's living in the first place? And we'll check those out starting on Monday. Take care. Hope you have a fantastic Thursday. Remember to take those quizzes, and I'll see you online and in the classroom. Bye-bye.